what we had in a previous lesson is that residuals equals error, or error equals residuals. They mean the same thing. And what we're doing here is we're actually going to look for patterns within that error, that we're going to quantify it, graph it, and see what it tells us about the nature of our relationship. Is it what we expected it to be, or is it different, or what are some hidden things we might not normally see? So you do have fill-in notes, and that would be on page 12 of your packet. I'm afraid you have to write this one out. So residual is just difference between the observed value of the response variable and the value predicted by the regression line. And this is just saying the same thing a little bit more packed together. Observed y minus predicted y, y minus y hat. Remember, e equal y minus y hat? We had that in an earlier lesson. So yeah, it's back to haunt us yet again. So maybe if you're writing this, you can pause, but I'm going to continue. All right. The issue with your error or with your residuals is that when you put a least squares regression line into your scatter plot, you're putting the absolute best line of best fit in there. You know, it's a mathematical model. It minimizes the sum of the squares of the error. So what you end up with is just a certain amount of error that's cut exactly in half. Half the error is positive, half the error is negative. So half of it exists above your regression line, half below. If you add it all up, you get 0. And if you average it up, you get 0. So yeah, that's a feature. So when you, well, we'll get to this. Hang on. So a residual plot, this is like a scatter plot. It's just a special one, and it's going to let us assess how well that LSRL served to model the data that we have. Maybe it's great, maybe it's not. So if you're hand graphing, which you won't do much of, but there is one in the homework, the horizontal axis is the same horizontal axis as your scatter plot. Same variable, same domain values, same scale, same everything. The vertical axis, however, is just going to be your residuals or the error. That's what you're going to plot there. And since some of it will be positive and some of it will be negative, you want a horizontal line at y equals 0 so that you can have sort of a frame of reference to note, you know, where the positives are, where the negatives are, and occasionally you get one right on the line where your error is 0. So you need all three of those things. Okay, so we are going to do this on a calculator so you can improve your calculator skills. And so what I need for you to do is to label age on your, in your first column in a spreadsheet. Put those in, age, 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 and then score goes in the second one. Right? This is the age when a child first speaks, their first word, and this is in months. So you're looking at really young kids, 9 months, 8 months, 10 months. A Jessel test is like an IQ test for little kids. Don't quite know what they do, but apparently it's supposed to measure their smarts. So what I'm going to do is we're going to just stop here and pick up the PowerPoint after we do the computer stuff. So you may need to pause this. All this data is on page 13. So if you need to get it off of a piece of paper, like I prefer that, maybe you can go there. But I'm going to move forward, and I have got my data already entered. So get caught up with me and follow along. So the first thing I would probably do is graph this thing. That seems to be always the best option for a first thing to do. And I believe that our explanatory was age at first word spoken to predict the score on this test. And wow, it comes up looking funny, right? It does seem to be linear. It's clearly negative. But I think at best I would just say moderate for the strength of the relationship. it's not great. And not only is it not great, but look, we got something that's sort of out by itself in the vertical, and we have something that's displaced on the horizontal, this point here. Now, while you may think that this point is lining up pretty well, if we take that point out, things are going to change probably pretty markedly. But for right now, let's go ahead and do the next thing we might do, which would be to throw in the regression line. So I'm going to analyze that with a regression and show linear a plus bx. And there it is. The only thing it's missing is the hat and the context. And there's your line of best fit. All right. So, but that's really not good enough because there's no r or r squared. So I'm going to go back home and I'm going to go over to a calculator page. You know, you can do your linear regressions and a lot of these things in the cell sheet or in the, why can't I think of the word, but your cell sheet. But I like to do it on a separate page. So anyway, so menu, statistics, stat calc, linear regression, a plus bx. Remember, age was explanatory. Score is your response. Leave the F1 there, that's important. Go down to OK and hit enter. And there everything is. Now if you look at your coefficient of determination here, your r squared, that's pretty low. And so what it's telling you is that only 40% of the variation in the that Jessel test score can be explained by the variation in age. So these two variables are only about 41% related to each other. And that ain't much, right? The R gives you the negative, so you can, you know, it matches up with a negative slope and everything. See, there's A, there's B is negative. And you have this thing called resid. And that's just telling you they've been calculated. Now, if you want to see them, what you can do is type, watch this, STAT period, and this pops up. And you can pick a whole bunch of things that go with stat, and I'm just going to grab resid. And see how it got dark? That means, yeah, those are waiting to be shown. So hit enter, and there they all are. And some are positive, some are negative. They should all add up to 1. Now, if you want these in your, your spreadsheet, then you're going to have to pull off a little trick that a student in my 3rd period class figured out for me. That's cool. So arrow up to select it and hit enter. That makes it active. Then we want to store it. So remember, control var is store, see the little STO. So control var, see the arrow, and we'll just store it with a letter. We'll store it as A. And we'll hit enter. So now it's stored. If you want that in your cell sheet, then just, here's another trick I can show you. If you hit control and arrow up, see how those little little dots up there, they stand for a window that you could be in, and you can open them all up. Mine are all open. This is the one that's selected. I can actually delete it if I want. I'm just going to move back into my spreadsheet and hit enter. And I need the 3rd column because I want those residuals to show up. So up, 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 up. Okay, got a little ways to go. And I'm just going to type RES in there for a name. And I'm just going to go ahead and do equals, because I need a formula here, A. And just go ahead and hit enter. And I don't want a column reference like this A. I want the variable reference. And hit OK. And there they all are. Now the point in doing this is it's kind of fun to see if the things add up to 0. So I'm going to do control and arrow up again, and I need to go back into my calculator page, so back to it and hit enter. And all you have to do is type sum, S-U-M, with parentheses, and what was it, R-E-S was my column reference. See how it went dark? And just hit enter. And now that is not exactly 0, but yeah, 11 zeros and an 8, 6, that's just rounding. So they do add up to 0, in case you were wondering. All right, but we still don't have a residual plot. If you're here, then you can do it very easily on your original graph. So I'm going to go to it. That's this in the middle. So scoot over and enter. And the easiest thing that you can do here is to go ahead and go to your response variable and click it. And so long as you have done your regression, you can just go down to this stat resid. Stat resid. So we're going to change that. Remember, that's your error, and that goes on the vertical, and your x value goes, or your explanatory goes on the horizontal. So there it is. All right. So this is that one that was displaced in the vertical. This is the one that was displaced in the horizontal. Otherwise, it's linear. Okay, it's not the best with linear I've ever seen, but it's really not a curved relationship either. So we're just going to go ahead with that. Now, if you have to reproduce it, you can just copy this down onto a piece of paper. All right. So that's your residual plot. Now, there is another option that I thought I would show you, and let me show that to you. So let's just say you're here. Another cool option, and I don't use this as much just because it gets kind of squished, but you can go to Menu and Analyze and Residuals and show residual plot. And see, you get your original scatter plot with the residual plot below it. As I said, that's a little squished for my taste, but it is there for you. So I'm just going to kind of undo that. So I'm going to hide that. All right, so let's minimize this and go back to the PowerPoint. I can't think of anything else I could possibly show you. So getting back to it, this is where we left off. And so let's see what these residual plots are supposed to tell us. Okay, a good linear model looks like this. See this kind of random scatter all about the zero error line? That uniform scatter of points indicates that that regression line fits your data really well. And since you are saying it's linear, then you can claim that a linear model is good. All right? So nothing really interesting here. It's just, okay, I thought it was linear. Yep, it's linear. So what isn't so good? All right, you see this curve right here? This big arching curve? And it could curve this way, or it could look like a J. You don't want to look for little bitty curves like, ooh, look, there's a curve, and wow, there's one here. See that? No, 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 no. You want something large like this. All right, if you get something like this, your data set was never linear to begin with. It's some kind of a curved relationship. And it is possible not to see that in a scatter plot, you know. So, yeah, but you do catch it here. And what that means is you need to stop what you're doing, quit doing linear procedures with it, and find another model and work with it that way. And we're not ready to do curve models yet, but yeah, this is some kind of a clue that you need to be analyzing this in a curved model environment. All right, here what you've got is right down here on the left, you got very little error. See, close, close, close. All these are close to the zero line, but as you move to the right, see how it's fanning out more and getting more and more kind of unstable and spread out, more variation. All right, what's happening here is you're going to get really good predictions on the low end and not such reliable ones on the high end. So you got kind of this not consistent scatter plot throughout the whole domain of your values. All right, and it could be that you got all the spread here and it'll be tight on the other side. So that could happen too. All right, in your data set, we're going to call an outlier, you know, something that's displaced in the vertical. Although we're not going to be married to this too much. This is displaced in the vertical, that's displaced in the vertical too. All right? However, you can get things that are displaced in the x direction. All right? And if that happens, which we saw in that scatter plot we made on the calculator, you're going to have points that are considered to be high leverage. They look like they work, but they're going to be a problem. When you have a point with high leverage, it has the potential to change your regression line. So it can change that, it can change R, it can change R squared. Those things are sensitive to unusual values, like they're non-resistant. Remember that term? So there's another set of 3 things that you can throw in there with non-resistant, with range and standard deviation and variance and mean. Okay. It is possible to have a high leverage point that's also an outlier. It could be displaced in both directions at once. So that makes naming it a little bit shaky. If you encounter something that you're not quite sure of what to name, just call it influential, because omitting it from your data analysis would give a very different model. So it's influencing what you're looking at, maybe not in a good way. So both high leverage points and outliers can be considered as being influential because removing either will change the regression line. You change it, you change R, you change R squared, you change your predictions, everything changes. So when you have these weird points, you got to make up your mind if they should stay. Now don't just get rid of them because you don't like them or that you think they're bad. You know, they may need to be there, but maybe they're an error. Maybe it's just a data entry error. Who knows? So here was the original scatter plot. It looks a lot nicer in this drawing than it did on the calculator screen. But so there's your outlier displaced in the y direction. There is your one that's displaced in the x direction. Come on, brain, it's late. High leverage point. We used to call it something else, so I'm a little slow on the uptake. You might say to yourself, yeah, but how can that exert influence? It's right in line with all the other ones. Say you take that out. Isn't that attracting that line to it? So if that's gone, this line will snap up a little bit, and that'll make a big change in your predictions. That's why it's high leverage and influential. And here's the residual plot. We looked at that too. It really clearly shows the outlier, and it really clearly shows the one displaced on X. And yeah, so you can't miss it.